In this section, we're going to discuss about the emergence of nanomaterials. We're going to touch few important milestones in the advancement of nanomaterials. So you might be wondering how in the sudden the researchers start to work in this field. To answer this question, we need to go back a little bit in history. More than 150 years ago, in 1857, Michael Faraday synthesized the first gold colloids of nano-sized. Michael Faraday is one of the most influential scientists in history because of his contribution in many new concepts such as electrolysis, liquefaction of gases, catalysis, discovery of benzene, electricity, various forms of magnetism, diamagnetism, paramagnetism, diffusion principle of candle flame, cathode ray, and also the foundation of the field theory. Faraday spent a significant amount of his time in the mid-1850s investigating the properties of light and matter. He made several hundred gold slides and examined them by shining light through them. To make the gold leaf thin enough to be transparent, Faraday had to use chemical means rather than mechanical. Part of this process involved washing the films of gold, which Faraday noticed produced a faint ruby-colored fluid. He kept samples of the fluid in the bottles and used them for similar experiments, which is shining a beam of light through the liquid. The light has been scattered because the fluid contained suspended gold particles that were too small to be seen with the scientific apparatus of the time. This effect is known as Faraday-Tyndall effect, and it is because of this discovery that Faraday is seen as one of the first researchers into nanoscience and nanotechnology. In 1915, William Oswald, a famous chemist, wrote a book with the title of Word of Neglected Dimension in the German language. And in the book, he urged scientists at the time to start looking into the smaller scale. At that time, the main focus has been on the old quantum theory, which starts earlier in 1900 to 1925. So many scientists more focusing on the theoretical parts of quantum mechanics and creating new experimental to prove or to explore the quantum mechanics. Based on the William Oswald suggestion, I guess, in 1931, Ernst Ruska and Max Knoll developed the first electron microscope. Electron microscope is a microscope that uses a beam of accelerated electrons as a source of illumination, as the wavelength of an electron can be up to 100,000 times shorter than the visible light. Electron microscope can have a higher resolving power than light microscope and can reveal the structure of much smaller objects. But of course, the first prototype that Ernst and Max developed has very limited resolution. But after 2 years, in 1933, he came out with a next prototype that is capable to match the optical microscope resolution. Even though since then the design of the electron microscope has evolved a lot until this day, but the commercial scanning electron microscope are still using the same design as the first prototype that Ernst and Max developed in 1931. The invention of electron microscope really accelerated the progress in nanotechnology field, since the scientists now can see the nano world that they are working with. 20 years after that, in 1951, Erwin Muller developed field ion microscope. Field ion microscope is another technique that can be used to see the nano world. Unlike conventional microscope, where the spatial resolution is limited by the wavelength of the particles which are used for imaging, the field ion microscope is a projection type microscope with atomic resolution and approximate magnification of a few million times. The invention of the field ion microscope marked the first occasion that a human can see an atom. He wrote in his book the following sentence: "It was a sticky day in August 1955 that I became the first person to see an atom." And the field ion microscope works based on his own principle of field desorption. The image on the right shows a field ion microscope image of tungsten. So each of the bright spot is actually a single or individual tungsten atom that shows its crystal structure. 1959 marked another arguably milestone in the progress of nanotechnology with the famous talk or lecture given by a famous physicist, Richard Feynman. The title of the lecture is "There's Plenty of Room at the Bottom." He is often credited for introducing the concept of nanotechnology about 60 years ago. He gave the lecture in the annual meeting of the American Physical Society at California Institute of Technology on 26 December 1959. In his talk, he suggested that it would be possible to arrange the atom the way that we want. So there he said, a physicist should be able to synthesize any chemical substance by putting the atoms down where the chemist says. He also discussed various aspects of miniaturization, likely challenges, and how to overcome it. In many ways, actually, the scientists and the researchers nowadays are doing or facing the same challenges as what Feynman has discussed more than 60 years ago. In 1968, Alfred E. Chu and John Arthur developed molecular. In 1968, Alfred E. Chu and John Arthur developed molecular beam epitaxy technique, or in short MBE, that is used for layer by layer growth of materials, specifically for the growth of single crystal epitaxial films on a hot substrate from molecular beam under ultra-high vacuum. MBE is widely used in the manufacture of semiconductor devices, including transistors, diodes, and whatnot. And it is considered one of the fundamental tools for the development of nanotechnologies. In 1970, Leo Esaki, a Japanese physicist that won the Nobel Prize in 1973, demonstrated the quantum size effect in semiconductor. In early years of semiconductor optoelectronics, the bandgap that could be achieved were largely determined by the physical properties of key 3-5 materials like gallium arsenide and its alloy, such as aluminum gallium arsenide and indium gallium arsenide. Then in 1970, a major breakthrough occurred when Esaki invented the semiconductor quantum well and superlattice. He realized that the development in the epitaxial crystal growth could open the door to new structure that exploit the quantum confinement or the quantum size effect. Quantum confinement effect is observed when the size of the particle is too small to be compared to the wavelength of the electron. The word confinement means to confine the motion of randomly moving electron to restrict its motion in specific energy levels. As the size of a particle decreases until we reach a nanoscale, the decrease in the confining dimension makes the energy level become discrete, and this increase or widen up the band gap, and ultimately the band gap energy also increases. In 1980, Akimov, a Russian scientist, showed the same quantum size effect as Leo Esaki, but this time in cadmium sulfide and cadmium selenide particles instead of epitaxial layer or thin film. Based on the concept of quantum confinement, which is over the barrier, which is now the surface of nanoparticle, the optical properties of cadmium selenide nanoparticle changes with size. As can be seen in the image here, if the size of cadmium selenide is 4.2 nanometer, it will become red. And if you decrease the size of the cadmium selenide particles into 3.9 nanometer, it will turn orange. And at 3 nanometer, it will become yellow. At 2.5 nanometer, it will become green. And at 2 nanometer, it will become blue. This triggered the research on nanoparticles, especially in the semiconductor and various metal nanoparticles. In 1981, Gerd Bennig and Hendrik Rohrer developed the scanning tunneling microscope, or in short STM, by which atomic resolution now can be obtained. This is a good example of the special attribute of nanoscale, where the quantum mechanics meet the classical mechanics through the concept of quantum tunneling. For STM, good resolution is considered to be 0.1 nanometer lateral resolution and 0.01 nanometer in terms of the depth resolution. So with this resolution, the individual atom within material are not only can be imaged, but we can actually manipulate each and every one of them. This invention of STM is followed by a family of scanning probe microscope of various types soon after that. 1985 marks the synthesis of the first carbon nanomaterials by Robert Curl, Harold Kroto, and Richard Smalley, which is a 60-atom carbon molecule later named as fullerene. Fullerene is an allotrope of carbon whose molecule consists of carbon atoms connected by single and double bonds, so to form a closed or partially closed mesh with fused rings of 5 to 7 atoms. Actually, fullerene had been predicted for some time, but only after their accidental synthesis in 1985 they were detected in nature, and now they also have been detected in the outer space. In 1989, Don Igler wrote letters of IBM. You know, IBM is an electronic company using xenon atoms. Each individual dot here is an atom of xenon, and such a precision writing were made possible by the technology capable of manipulating individual atoms, which has been invented earlier, which is the STM. Here, STM was used to arrange 35 individual xenon atoms on a substrate of chilled crystal of nickel. In 1991, Sumio Uejima discovered another carbon allotropes named as carbon nanotube. As supposed to be a sphere, carbon nanotube is a cylindrical molecules that consists of a sheet of a single layer carbon atoms. They can be single wall and also a multi-wall carbon nanotube, and its diameter can be more than 100 nanometer, but their length can reach several micrometers or even millimeters. The most interesting about carbon nanotube is its mechanical properties as one of the strongest materials in the nature. 8 years later, in 1999, Chad Merkin developed the synthesis technique called deep pen lithography. As the name suggests, deep pen lithography used a similar concept with a deep pen or quill pen, but instead of using the tip of a feather, they used the tip of AFM, atomic force microscope, which we call it cantilever. This technique is still used for various applications in chemistry, material science, and life sciences. Roughly 10 years after Don Igler wrote the letter of IBM using xenon atom, in the year of 2000, he devised or revised the quantum mirage using ferrum atom on the copper substrates. So now the barrier, which he called quantum corals, are constructed by individually positioning ferrum atoms, or adatoms in this case, using the tip of a cooled scanning tunneling microscope. In 2006, we have two important milestones in the field of nanotechnology. The first is with the development of a nano car by James Tour and colleagues from Rice University. They built a nanoscale car made of oligophenylene ethylene with alkynyl axles and 4 spherical 660 fullerene as the wheels. The car actually can move like conventional car. Secondly, in the same year, IBM created a nano word map, the word map with a nanoscale size. IBM used a silicon tip measuring only few nanometers at its apex to chisel away materials from a substrate to create a complete nanoscale 3D relief map of the world within 2 minutes and 23 seconds. Most recently, in 2009, Nedrian Seaman and colleagues in New York University created several DNA-like robotic nanoscale assembly devices. It is a process for creating 3D DNA structure using synthetic sequence of DNA crystals, replicating the size and shape of the actual DNA. The DNA-like robot can be programmed to self-assemble using sticky ends and placement in the set order and orientation. Using clever chemistry, the robot actually can assemble themselves. And now, nanomaterial has been used almost everywhere and benefit various research fields and ton of applications such as in chemistry, electronics, high-density magnetic recording media, sensors, biotechnology, medicine, and etc. From research point of view, nano-sized material now emerge as one of the focal points of modern research. We are achieving astonishing ability to design, synthesis, and manipulate structures at the nanoscale in order to achieve or to create a unique set of properties that we have determined, such as optical, electrical, magnetic properties, catalytic, biological, or mechanical properties. And in fact, it is anticipated that in the next few years, there will be no aspect of life untouched by nanotechnology. The figure here shows the estimated global nanotechnology market size from the year 2010 until 2020. The market size, as you can see from here, growing exponentially, especially in the few years back, starting in 2016. It is predicted that the global nanotechnology market size will surpass $100 billion in 2020. That's all for this section. See you in the next session where we'll talk about the main motivation of the progress of research and also the development in the nanomaterials. Thank you.